Sorry about it. So we will discuss about the cement this week. So we will first see what do we mean by, like, why it is important to learn about cement. So cement is a binder which is used to bind aggregates together in the rigid pavement. So we have two types of pavements, rigid and flexible. So we use cement to bind the aggregates in the rigid pavement, and we use bitumen to bind the aggregates in the flexible pavement. So that's the main difference between the rigid and flexible pavement, the binder that we use to bind the aggregates. When we look at the inorganic cements, we can divide them into two categories, hydraulic cement and non-hydraulic cement. The main difference between the hydraulic and the non-hydraulic is hydraulic cement get hardened with the reaction with the water. So set and become adhesive due to a chemical reaction between the dry ingredients and the water. So that's the main type of cement that we use. And Portland cement is an example, and Portland is a trade name, but however we call the cement as Portland cement, not main like we are used to call the hydraulic cement as Portland cement. Non-hydraulic cement does not set in wet conditions or underwater. It sets as it dries and reacts with carbon dioxide in the air. So we need sometimes, we have to do construction in underwater construction. So in that case, if the cement is get hardened due to water, it will be a problem. So this non-hydraulic cement used for that kind of applications, and the hardening of cement is happening not because of the reaction with the water, that is happening due to the reaction with the carbon dioxide. So we are not going to learn this because we are looking at the pavement construction. So we will look at the hydraulic cements. So we will discuss about the Portland cement production, chemical composition of Portland cement. Portland, the trade name is for the hydraulic cement. Okay, so Portland, wherever we have Portland, though it is a trade name, we consider that as the hydraulic cement. So hydration of cement, hydration is the chemical reaction between the cement and water. When we add water to cement, that reaction starts, and we will learn about the reaction because it is important. Depending on the ingredients in the chemical composition of the Portland cement, different cements have different compositions. Depending on what chemicals we have, this hydration process will generate different amount of heat. It will get hardened in different times. So some are fast hardening, some has delayed hardening. So we need to learn about this reaction process to understand that, to select the right cement for a particular application. We'll discuss about the properties of cement, supplementary cementatious materials that we can use in a cement, different types of cements, and also admixtures that we can use to improve the quality of cement. So these are the 7 things that we will learn. Let's start with the Portland cement manufacturing process. So cement is main ingredient in cement is the limestone. So we take limestone from the quarry and then we crush it, then we store it, then we have to mill it to small particles, then we burn it in a kiln. This kiln will go to a very high temperature, 2300 kelvins or something like that. And in the kiln, limestone is burning, and we get the product as clinker. So this, when we burn the limestone at a very high temperature, some reactions are happening inside it, and that the outcome will be the clinker. So we store the clinker, then we have to grind this clinker to very small powdery particles, and then we have mixing processes as well. If we have admixtures to mix, we have to mix here before we pack it in packets. And also here we are adding gypsum we will learn why we need gypsum. So mainly the main ingredients in the cement is the limestone. When the limestone burn in a kiln, it will produce the clinker. So we just call clinker when it is burnt, limestone burnt, we call it clinker. And clinker can have different chemical compositions depending on the reactions happen, and depending on the quality of the limestone, the clinker, different batches of clinker can have different chemical composition. So depending on that, the properties of the cement will be different. So we will learn about it. So cement clinker is made by prior processing of kiln. That means the materials are subjected to high temperature in order to bring about a chemical or physical change of the kiln feed into a preheated kiln system. Output from the kiln is called the clinker. Clinker consists of 4 components as follows. So before that, I wanted to tell you, so preheating, to save the energy here, we can see I have had experience in a cement manufacturing plant. That was my undergraduate training. I was in a plant for 3 months. I was there. I had to stay there the 3 months. Only weekends I was able to come home. So so it's very interesting part of mine as well. So here we preheat the limestone before coming to the clinker by using the gas here coming out from the kiln. So we save the energy in that way. So we use, and also here when it is preheated, it will be more efficiently burning in the kiln. And the 4 chemical compounds in clinker are tricalcium silicate. Hereafter, we mainly call it C3S, tricalcium silicate. Dicalcium silicate, so we call it C2S. Tricalcium aluminate, C3A. Tetracalcium aluminoferrite, that is C4AF. So you have to be familiarized with these 4 abbreviations: C3S, C2S, C3A, and C4AF. These 4 compounds are known as the main crystalline phase of Portland cement. So clinker look like this. They are black particles like this. We need to grind it to the powdery form to get cement. So chemical compounds of Portland cement, you should be able to familiarize these words. And in the tutorial, they are asking you to write these chemical compound and the common formula. And also, it's good to remember this full chemical formula. This is the abbreviation C3S, but C stands for calcium oxide and H stands for silicon dioxide. So you can see 3 calcium oxide dot silicon dioxide this is the full chemical formula. So C2S can be written like this, and C3A has calcium oxide and aluminum oxide, and tetra calcium aluminate will be like this. So you can remember, mainly I want you guys to remember this because we are going to use these abbreviations more oftenly. And you can see the usage range by weight. This is not the exact percentages. We can have different cement can have different percentages of these 4 compounds, but you can see here mainly in a cement we have C3S. So the C3S component is is in the higher percentage. Then C2S 15 to 30, C3A 6 to 12, and C4AF 6 to 8. So these are the general composition in clinker. So these 4 compounds are responsible for different actions in a cement. So C3S contribute to early strength development of hydrated cement paste. So when you have a cement with a higher amount of C3S, that one is reacting with water fast, and that will get set fast. So there are some applications we need to get a fast setting cement. You may have heard if you go to Bunnings, we have quick set cement. So uh, in those cements, we have more C3S. There are other reasons as well. We can add admixtures to get fasten this reaction. We will learn about those things later on, and also cement particle size is important for the reaction. So please keep those apart. We will learn them later. When you look at the four components, when you have C3S is higher, then it will contribute to early strength gain. And C2S is delaying. If you have a cement with comparatively, if you compare two cements, and if you see in a one cement, you have less C2S, that cement is having the property of late strength development. There are situations we need to delay the setting. If your mixing plant is far away from your site, you don't want the cement to get hardened on the way of the delivery, so you have to delay it. And also sometimes, like in a hot summer day, cement get hardened quicker because of the environmental temperature. So you need to, before you pour into the cast, into your formwork, cement, if the cement is get hardened, then it will be a problem. So you have to sometimes delay the strength gain. So in that case, we need to select a cement with higher C2S. Again, this is not the only thing which decide the late strength development. Admixtures can be there, so we can add admixtures to delay the hardening, and also particle size of the cement also important. If the particle size is large, then the reaction will be slow. And C3A is an undesirable, since it makes hardened cement paste easy to be attracted by sulfate. So when you do construction in a contaminated land, if the soil is with contaminants, if the soil has sulfate, then this C3S can react with the sulfate. Or else if you are doing any construction in a sewer plant, again, the sulfate react with the C3A. When the sulfate react with the C3A, what is happening is this concrete will become swollen. So that so we have to select a cement with less C3A when we have contaminated land. So when we have an environment with sulfate rich. And also there are other precautions as well. We can't get rid of C3A by, like, to 0%. It is happening. This four things are generated when in the kiln, when you burn limestone, when it becoming clinker. So we can't make it to 0, but we can select a cement with less C3A. And also there are other precautions. I will explain them later. So there we can have admixtures, or else we can have air and train concrete. Don't worry about those things for the time being. Just remember that when we have C3A, a higher amount of C3A, then it will be, if you are using that cement in a sulfate affected area, that will be a problem, because it will make the concrete swollen. But it will facilitate combination of the lime and silica during the cement manufacturing. So it has an advantage as well during the cement manufacturing process. C4AF reacts with gypsum and accelerate the hydration of silicates. However, if you can see, the main component that we have is C3S. So, and then the next one is C2S. If you remember, we can see 45 to 60% is C3S and 15 to 30% is C2S. And these two are very less amount. We have very less amount. So even though, like, in some situations, these small amounts also critical. However, mainly these two are the two components that we have. Okay, so do you have any questions so far? Any question?
No, thanks, Yupika.
Okay, thanks. Okay, so as I have mentioned, cement with a high C3S is recommended for the repair of a busy highway to gain strength as quickly as possible. If you have to repair a busy highway, you can't close the highway for a long time because it's a busy highway. So you have to get it repaired quickly. So in that kind of situation, you have to use a cement with higher C3S. For a sewage project, cement with a low C3A is recommended to reduce the damage due to the concrete reaction with the sulfate. A cement with high C2S is recommended in a hot weather day to prevent hardening of the cement concrete quickly. So these are some of the examples. There are other examples as well. And you have, I'm going to open your quiz after this week. Then you can see there are other questions related to this one, this 4 things. So now let's see how we can find the amount of these 4 components in a cement. So we can't when we do test materials in a lab, we can't straight away find out how much of C3S there, how much of C2S there, like that. We can find the amount of oxides in the cement. So we can find how much of calcium oxide, how much of silicon dioxide. So we can find how much of these oxides we have. So when you know the percentages of these oxides in a cement, we can use these 4 equations. We call them Boeck equation. You don't need to remember these equations. You should be able to calculate the amount of C3S, C2S, C3A, and C4AF in a cement using these equations. So you have one question in the tutorial. You can try this. The only thing that it's not hard, if you know all these oxides, you can just put the numbers and do the question. The only thing that you need to remember is this whole part is if you look at the previous table, this is your C3S. To find the C2S, you have to find C3S and you need to substitute that part here. So amount of C3S times 0.754. You need to minus this amount from 2.87 times of silicon dioxide percentage. So remember this. Sometimes students go wrong when you are calculating the C2S. You have a question in the tutorial, you can try it. Now let's look at the hydration of cement. So hydration is these compounds that we talk about, C2S, C3S, C3S, and C4AF, when you add water to that, what is happening? This reaction we call the hydration reaction, and this process we call the hydration of cement. Now let's see what is happening. So when we add water, what is first happening is C3S rapidly reacts to release calcium ions, hydroxide ions, and the large amount of heat. So this reaction is rapidly happening and it is generating a huge amount of heat. The reaction slowly continues producing calcium and hydroxide ions until the system becomes saturated. Once this occurs, the calcium hydroxide starts to crystallize. Simultaneously, calcium silicate hydrate begins to form. Ions precipitate out of the solution, accelerating the reaction of tricalcium silicate to calcium and hydroxide ions. I will show you the reactions in a few minutes. Then what is happening is C2H also start to react, but this reaction is slow compared to the C3S reaction. So this is happening slowly. The other major components of Portland cement, tricalcium aluminate and C4AF also reacts with water. Their hydration chemistry is more complex as they involves reaction with the gypsum as well. It's not only reacting with the water, it is reacting with the gypsum as well. Gypsum is another material that we add to the cement. I told you we are adding gypsum to the cement because it's needed. I will show you what is happening with the gypsum reaction. So these are the reactions. You don't need to remember this, but you have to have an understanding of this. So tetracalcium silicate, that means C3S, when you add water, it will produce calcium silicate hydrate, silicate hydrate and the calcium hydroxide. Then dicalcium silicate with water, it is making calcium silicate hydrate and the calcium hydroxide. You can see again this C3S is reacting with the calcium hydroxide, which is produced here as an output. So it is reacting with this output again and making this calcium aluminate hydrate. And also tetra C4AF is reacting with water and also reacting with calcium hydroxide, and it is making calcium aluminoferrite hydrate. So calcium aluminate, again C3S, C3A is reacting with water and gypsum together, and it is making calcium monosulfonate hydrate. So you, as I told you, you don't need to remember these reactions. However, you need to have that understanding. These main components, C3S, C2S, C3A, C4AF, they are reacting with water and also products of this reaction. So this calcium hydroxide is a product and it is reacting here. You can see it is reacting with them again, and it is making the hydrate. So if you look at the right hand side, so these ones are again reacting. So all hydrates are remaining here. So these are the hydrates that we have when the reaction is completed, because these ones are reacting again. So these ones are, this part, calcium hydroxide is reacting again. See, so they are not like, the only things that remaining in the right hand side will be hydrates, all these hydrates, and those are the things we have. So here, if you look at the hydration process, this is very important. First thing is the wetting of the surface. So that's why I told, when the cement particles are very tiny, they have larger surface area. Like when you consider caster sugar and sugar, caster sugar is tiny particle and it is very easy to mix with water, or when you are baking something, you are using caster sugar because the reaction, or else it dissolve easily because the surface area is high. So if you consider normal sugar and caster sugar, you can see when you add all the surface areas together, this one has a higher surface area. The surface is wetting first and it is reacting faster. So that's why I said when the cement particles are small, this reaction is happening fast. So initially, this surface will get wet, and then it forming a gel like this, and then the setting is developed. So you can see these particles are getting hard. Then you can see a final set develop of rigid skeleton, and finally hardening the whole part. You can see with the days how the strength is gaining. So you can see C3S is gaining quickly the strength. So if you look at the 28 days, this is 28, we are testing the concrete in 28 days in most of the cases. So at 28 days, it has gained a higher amount, 50% or 50 megapascal of strength. In 1 year time, it is gaining 70 megapascal. So it is almost reaching more than a half of the strength in 28 days. But if you can see, C2 is also gaining the same strength like C3S in a year, but it's not gaining that much of it's gained the strength slowly. So at 28 days, you can see the strength is this much. So that's why if you use a cement with high C2S that will gain strength slowly. So it is delaying the hardening process. And C3A and C4AF is not contributing to the strength, but they are like, we have them in the reaction. And they have other things like, heat generation and the reaction with sulfate. So they are not contributing to the strength at all. But the two main parts that contribute to the concrete strength is C2S and C3S. Now let's look at the heat of hydration. If you look at here, you can see the joules per gram, how much of heat is generated. So C3S is generating 502 joules per gram. And also we said about 60% in a cement is C3S. So this heat gain is very high. So C3S is mainly the heat gaining the material which is chemical compound, which is contributed to the high heat gain. And also C3A, if you look at this one, 867 joules per gram. However, we have a small amount of C3A, so you can see the second peak is because of the C3A reaction. So heat generation, if you want to control the heat generation, there are some situations we need to control the heat generation. For example, if you consider a huge dam, a huge dam is a mass concrete. So we have a lot of concrete in that. So if we don't control the heat generation, what will happen is outer surface of the dam will get hardened quickly, and the inner material is getting hardened slowly. And this, when you know that when we heat up something, it is expanding, and when you cool down, it is contracting. So when during the cement hydration process, the concrete expands, and with the time, when it is cooled down, it is contract. So if we have these huge temperature differences in a mass concrete, what will happen is, due to these thermal expansions and contractions, that and also because the outer surface is getting hardened quickly, and the inner surface is getting inner material is getting hardened slowly, because of that, and also the heat generation, that contractions, due to these contractions, there can be thermal cracks. So there are some situations we need to control the heat generation. In that situation, we try to use a cement with less C3A and C3S. And also there are additives that we can use to reduce to control the heat generation. And also again, by selecting a cement with bigger particles compared to a tiny particle cement, again heat generation can be controlled. So this is how the heat is generated when we add water to cement. If you have experience, you may have felt it when you add water to cement. You can see that is getting it is an exothermic reaction. It produces heat. So you should have felt it if you have done concrete mixing. Do you guys have any question?
None from me, thanks, Yupika.
I hope Jaden is there. Okay, so let's.
Yeah.
Okay, that's good. So if you now let's look at the properties of cement. So fineness is a very important property. The particle size of cement is an important property that must be carefully controlled during the production. Since the hydration starts at the surface of the cement particles, the finer the cement particles, the larger the surface area and faster the hydration. I already told you this. Therefore, fine material result in faster strength development and a greater initial heat of hydration. However, increasing the fineness beyond the requirements increases the cost of production and can determine the quality of cement. So we can't like, we can control the fineness of the cement during the manufacturing process. We can mill it to a small particles if you want to fast, if we want to have the reaction happening faster. However, we can't do it beyond a certain limit because it will be very costly to make the particles smaller than a certain amount. So we have supplementary cementatious materials. Cement manufacturing process, if you look at it, it is very costly because of this kiln. We have to heat it to a very high temperature, so it is a very energy consuming production. So what we can do is we can add some cementatious material. Cementatious means the bonding ability. We can add some other cementatious materials to reduce the cost. But it depends, like, when you add it, it can affect the other properties like the strength, or else the reactions and other things. However, in certain applications, we can use these materials with added supplementary cementatious materials to reduce the cost. So and also sometimes the cementatious materials can improve the quality of cement, because we can select these cementatious materials, very tiny particles, so it will improve some properties. So let's go through this. So cementatious materials we can use to improve consistency and the workability. Workability is how easy to mix the concrete mix. So when you have workability of concrete is depend on many things, depend on the cement, depend on the aggregates. When we do the concrete mix design, I will explain you more about it. So when you have rounded particles of aggregates, it is easy to mix. But when you have irregular particles of aggregates, then it is hard to mix. So there are, and also if you add more water, it is easy to mix, so we call it more workable. And if you have less amount of water, then it is hard for you to mix the concrete. It's like, you are making bread and you're making a cake. So in a bread, it's hard for you to mix the dough because you have less amount of water. But if you look at your cake mixing, you have a watery solution, so it's easy to mix. So workability is important. So we can have cementatious materials to improve the consistency and also the workability of fresh concrete. Fresh concrete is before getting hardened. Hardened concrete is the concrete which has got hardened. So improve consistency and the workability of fresh concrete due to the high cohesiveness. So cohesiveness is the ability to get together with the other particles. So some materials delay concrete hardening and acts as a retardant. So the materials that can delay the hardening, we call them retardants. The materials which can improve the hardening, that means it accelerate hardening, we call them accelerants. Accelerants and retardants are two opposite properties, have two opposite properties. So some of the cementatious materials can delay the hardening, so we can use it as a retardant. And it controls bleeding. Bleeding is when you pour the concrete. If you don't have a correct mix design, what happens is aggregates will go to the bottom and just the cement and water will stay at the top. So this we call the bleeding, and it is not it's not a good thing. We need to have a consistent concrete mix, because when you have bleeding in the concrete, you can see these particles are coming out, and also there is no enough bond between the aggregates at the bottom. So bleeding need to be controlled. We will learn how to do it later on as well. So having cementatious materials can control the bleeding. And also it controls heat generation and cracking, and also it reduces cost, as I have mentioned. So mainly cementatious materials can be slag, Class C fly ash, these are industry byproducts. So they are easy for us to, they are cheaper for us to use them. So fly ash, silica fume, so they are tiny particles compared to, especially silica fumes. They are tiny compared to cementarious materials, and it is used to improve the properties of cement depending on the application. So now let's see the types of cement. So we can have different types of cements, and you can buy this kind of cements in Bunnings as well. When you go to the cement section, you can see different types of quick set cement, this type, this. So when you go to Bunnings again, you please go to the cement section and have a look. So types of cement, we can have general purpose cements, that is a normal cement. And we can have general purpose limestone cement. That means we use a percentage of limestone in the cement. So limestone is before burning. So this we do to reduce cost, and also in some situations to improve the final look appearance. And this will reduce the strength of cement. But for example, if we do rendering of a house, we don't need that much of strength, but we need the nicer, smooth looking. So in that case, general purpose limestone cement is cheaper, and also it gives us an improved aesthetic appearance. General purpose blended cement is blending different cements together and improve the properties. Depending on our need, we do blend the cements together. Special purpose cement are for different purposes. For example, we can have high early strength cement, type HE. So you can see these ones have different abbreviations. GP is the general purpose, GL is general purpose limestone, GB is general purpose blended, and HE is high early strength. So to get the high early strength, we can have C3S, higher amount of C3S, or maybe we can have we can have small particles, or else we can have additives. Additives can be cementarious materials, or else we can have accelerants as well. So this cement we call, either you can have more C3S, small particle size, or additives added, and we make a cement, maybe combination of all three, and we call that cement the high early strength cement. You can find this in Bunnings. So you also can have low heat cement. In some situations, I told you we need to control the heat generation. So in that kind of situations, we use cement, this one, LH. So this cement can be produced by having less amount of C3A, because, sorry, C3A is giving a higher C3A, less C3A, and also we have moderate particle size, not very tiny particles, so we can control the particle size to have not very tiny, and also we can have additives to heat control, and we can make this cement in this way. And also we can have sulfate resisting cement, SR. Again, we should have C4AF, less amount of this one. Sorry. We should have C3A, less amount of this one, because it is the one which is reacting with sulfate and generating, make the concrete swollen. And also we can have some additives to control the sulfate reaction. Also, we can have shrinkage limited cements. So I told you, concrete, when it's set, it produces a heat, and with the time it will cool down and the concrete is contracting. So in some situations, we need to control this shrinking. We call this shrinking. For example, if you are building a bridge, you have to control the shrinking because it's a long path. If you have just a small percentage of shrinkage, that will reduce the total length of this one. So it will be a considerable amount. So we need to control the shrinkage in some situations. So in that case, we need to use the shrinkage limited cements. Are we good? Any question?
Nothing from me, thank you.
I'm all good. Thanks.
Okay, now let's see the admixtures that we can use. Admixtures are materials other than cement, aggregates, and the water that may be added to impact the specific quality to the fresh mix or to the hardened concrete. Admixtures are added at the time of mixing of fresh concrete, usually less than 5% of cement, to achieve desired properties. Purpose of using the admixtures are to increase the workability. We can have plasticizers and super plasticizers to control the workability. Sometimes when we do the concrete mix design, you will see we have to control the amount of water added to a concrete mix, because if we add more water, that will affect the strength. But when you have less amount of water, it is hard for you to do the mixing. So we need something to improve the workability without adding water. So we can add these admixtures, like they call them plasticizers and super plasticizers. They are acting as a lubricant. So when you add a little bit of oil to something in a we call in a bread dough, it will be easier for you to mix. Likewise, this plasticizers and super plasticizers are acting as a lubricant, and it improves the workability of fresh concrete. And also we can have some additives to delay or accelerate the reaction, to get hardened quicker or delay the hardening. So we call accelerants to accelerate the hardening reactions, and retardant to delay the hardening reaction. So we can have admixtures for this as well. We can have admixtures to reduce bleeding, to increase the strength of hardened concrete. Also, we can have to obtain concrete with less permeability. In some situations, we need to we need to have the permeability. In most of the situations, we need to control the permeability, because permeability is the force that you have in a concrete. So this will affect the strength. And also it will damage the concrete, because this permeable, if the concrete is permeable, water can move through the concrete and it will affect the durability. So we can add some tiny materials, additives, to control this permeability. However, in some situations, we need to have a certain amount of voids in a concrete. We will learn that when we do the concrete mix design. So we can have some additives to get rid of the permeability, and also there are some additives to create some voids in a concrete mix for special cases. We will learn about these special cases later. To increase the durability of concrete, we can have admixtures, and also to save money, we can have admixtures. So these are the purposes of admixtures. So we can have mineral admixtures and also chemical admixtures. So mineral admixtures can be cementanious materials. We already talked about the cementanious materials. We can have pozzolanic materials, non-reactive materials. So these are some of the mineral admixtures. So supplementary cementanious materials are fly ash, ground, granulated iron, balsa furnace, slag, and amorphous silica. Pozzolanic materials are materials with little or no cementitious properties, but react chemically with calcium hydroxide at ordinary temperatures to form compounds possessing cementitious properties. And examples are non-reactive materials are ground limestone, silica fume, and hydrated lime. So they are the examples of non-reactive materials. So these ones are some of these examples. So air-entrained agents, chemical admixtures are air-entrained agents. I told you some situations we need to purposely create voids in the concrete mix. So we have to add an air-entrained agent to evenly create the voids throughout the concrete. And set control admixtures, they are the retardants and the accelerants. And also plasticizing admixtures, plasticizers and superplasticizers to improve the workability. So these chemical admixtures are to improve get their voids, and also to set control, and also to improve the workability. So depending on our need, we can add these admixtures when we are mixing the concrete, but it should be less than 5% of the cement. So I told before as well. Okay, so this is the end. So Portland cement, we discuss about the definition, raw materials, oxide compositions, main components in there and their functions, and also the equation to find the 4 compounds, C3S, C2S, C3A, C4AF. And then we discuss about the hydration. What do we mean by the cement hydration? That's the reaction with the water. Development of structure in Portland cement paste. So we discuss about the strength gain and the heat produced. So these are very important. How the heat is gaining, and also how the strength is developing. And also we discuss about 7 types of cement and their composition characteristic and the major applications. We discuss about admixtures as well. So there are 4 questions in the tutorial. You can try them. As we have time, would you like to do they are very small theory questions. Would you like to do go through the tutorial as well with this one?
Yeah, I'd be happy to.
Are you okay with that, Haley? So we'll do the tutorial as well.
Yeah, I don't mind.
Okay, so this and this call. Okay, so let's go through the tutorial. In the tutorial, I have the summary. We'll go through the summary quickly as well. So we discuss about the types of cement. We have hydraulic and non-hydraulic cement. Hydraulic cement means it react with water and get hardened. Non-hydraulic cements are the cements which is not getting hardened with the reaction with water. Instead, it is reacting with carbon dioxide in the environment. So hydraulic cements can be high early strength, low heat, sulfate resisting, etc. So there are different types of hydraulic cements. Depending on our application, we need to select the right type. So to get the right type, we can have admixtures. We can select a cement with different composition of the 4 compounds, C3S, C2S, C4AF, and C3A. So these 4 components are responsible for different actions in the cement. So they are the main 4 components. So C3S is responsible for early strength gain. C2S is responsible for delaying the hydration process. C3A is reacting with sulfate, and it is a undesirable. So we have to make sure that we have less amount of C3A when we are working in an area with the sulfate. And also we discuss about the hydration of cement, what is happening when water is added to cement, that we call the hydration process. So properties of Portland cement, and also we discuss about that mixture. So these are the things we discuss. So the main material in the cement is limestone. Limestone is a natural material, and it is consist of calcium carbonate and the calcium oxide. And also we can have silicon oxide, we can add clay, and also we can have other materials as well, like gypsum, fly ash, slag, cementarious materials we can add to cement during the manufacturing process, and we burn it in a kiln, so we can have coal. And also there are research going on. This coal burning is very expensive, and there can be other things that we can have, like, industry byproducts, but we are still in the research stage, because this huge amount of heat cannot be produced with those materials sometimes. So but this coal is again a natural material, and it's non-renewable, like, it takes long time to have the coal, like, to naturally form coal. And also we discuss about the cement manufacturing. We mine the limestone, then we crushing, grinding, we homogenize it, and then we burn it in a kiln. Then the limestone will becoming clinker, then we'll grind the clinker and we get the cement. Okay, so these are the 4 chemical compounds. So we have C3S, C2S, C3A, C4AF, and we discuss about the composition in general, and also we discuss about the name and the full chemical formula. And I'm not going to go through this one because I already told you what they are doing. Hydration is when you add water, what is happening. So it is important to know about the strength gain and the heat generation. I told you this. Now let's look at the questions. What are the names, full chemical formula, and the abbreviation of 4 major compounds in Portland cement? Which compound contributes to the early strength gain, and which contribute to the late strength gain? So first part, just we'll do together. So can you tell me which compound is contributing to early strength gain? We have 4 compounds, C3S, C2S, C3A, C4AF. Which is contributing to the early strength gain?
Is it C3S?
Yes, that is C3S. How about the late strength gain? Which one is contributed to the late strength gain?
C2S.
Yes, that is C2S. Now let's see the formulas. You don't need to remember this. However, like, you have compounds, chemical formula, the common chemical name, they are asking us to write, so we can write it like this. So C3S is early strength gain, C2S is late strength gain, C3A is undesirable. It is easy to be attracted by sulfate. So, and C4AF accelerate the hydration. Second question is, what are the primary chemical reaction during the hydration of Portland cement? Write down the full chemical formulas and the hydration. You don't get these kind of questions, okay? Because you don't have to remember all these chemical reactions. However, I told you, you need to have the understanding what is happening. So that will be these are the chemical reactions. I had the full formulas in the lecture PowerPoint, and this one is the tutorial PowerPoint. I have this I have used the abbreviations in this one. all the PowerPoints are in your in views. If you go to the modules, at the bottom of the modules, you can see all tutorials and all lecture notes, PowerPoints of lectures. You can find them there. So you, as I have told you, you don't need to remember this, but you need to have an understanding of these reactions. Okay, now we have a numerical question. I want you to try this one, please. This is the only question that we have with numbers. So these are the 4 equations that we have. You normally, you have this in your quiz, and also you normally get a question, definitely get a question for your mid-quart as well, from these 4 equations. But if you do one question by yourself, you will be fine, because it's hard to go wrong. So you don't have to remember these equations. Equations are given to you to find how much of C3S, how much of percentage of C3S you have, C2S you have, C3A you have, C4AF you have in a cement. So in the question we have, as the third question, they have given us 2 cements, cement A and cement B, and asking us to recommend the cement to repair a busy highway. So to repair a busy highway, what kind of a cement that we use, that we should use?
One with more C3S.
Yes, so we need to have more C3S. So it can be a busy highway, or else it can be for any construction in a winter day, cold winter day. Why is that? In the winter day, the environment is cold. It's naturally it will get long time to get hardened. So you need to have a cement which is gaining strength earlier in a cold climate. And also, if you are doing a high-rise building, again, you have to get the strength quicker so that you can build the top floors. So this kind of applications, busy highway, any construction in a winter day, and also high-rise buildings. There are other examples as well. You need to have a cement with high C3S. Now, they have given you the cement A and B, and they have given you the oxides. But just by looking at the oxides, they are very close to each other. If you look at silicon dioxide, they are 24 and 22. So if you look at all this, they are very similar. So just by looking at the oxide compositions, we won't be able to recommend the cement with high C3S. Now we need to do the calculation. So let's do the calculation. So I have given you everything in this slide, and I'll give you a few minutes. Can you find me how much of C3S in A? How do you do that? I'll give you a few minutes, and I will do after you try by yourself.
So are we just looking for the C3S?
Yes,
Right.
because in this case, they're asking, you need to find the cement with high C3S.
Okay.
But in a question, if they ask you to recommend a cement for a sulfur affected area, are you going to calculate for C3S, or are you going to look at something else?
Is that one C4A?
C3A, sorry. It should be C3A, and you need to select the cement with less C3A for a sulfur affected area. And if I ask you to find the cement for where you have your mixing plant is far away from your site, that in that case you need to delay the hydration process. You don't want the cement to get hardened on the way. So in that case you need to find the cement with higher C2S. But in this particular situation, they are asking you to recommend the cement for repairing a busy highway. So in that case, you only need to find the C3S, and C3S in A and C3S in B, and then you have to recommend the one which has a higher C3S. So can you please find me the C3S in A?
Hey, Pika, for that one, I got 13.978.
Yes, that is right. How about you, Jaden? We'll wait for you. It's okay to go
Yeah,
wrong.
I got the same thing.
Okay, so you can do in the same way for the other one. And can you please tell me which one you recommend?
For cement B, I got 61.43.
How about you, Jaden?
Same thing.
Okay, so which one you recommend?
This cement B.
Yes, so you recommend cement B. So 14 because you got 13.9, so it's almost 15. So you recommend cement B for this particular one. I want one small thing for you to do. So C3S, you know how to find it, and all the other ones are okay. But I would want you to do this just for A. Just for A, can you find me C2S just for A? So A, consider A. 2.87 times 24.8 minus 0.754 times what? What should I put here? Should I do 3 times calcium oxide? That means 61.7 and times 24.8. Is this right or wrong? Is this right for this part?
No, I'm not sure.
No, why is that?
Because it's, I don't know.
This part is, if you look at, you just go to the first few slides and you.
Isn't that one's already C3S? So it would
Yes, so that is the expanded formula of C3S. C3S is the abbreviation. C3S is 3 times calcium oxide times silicon dioxide. So that is the abbreviation. So instead of having this is wrong. You need to have 13.9 or 14, which you have got there. Does that make sense?
Yeah.
Okay, so
So we need to remember.
yes, so
Or do we have those? Is that the full formula?
yes, this is the full formula.
Are we going to have those?
You will get these formulas you will get, but not with different colors. You get all in black. So you need,
And then we'll have the full chemical formulas as well for each of them.
chemical formulas. You don't get them.
So we need to remember them.
You don't need to remember, because this part, only thing you need to remember is this is your C3S.
Yeah, but we need to know what they are.
No, you don't get a question like that. For example, I told you.
Yeah, but like in this one, if you didn't know that C3.
Yes, then you will go wrong. Yeah.
Okay.
So this you need to remember.
Roughly.
Roughly, yes.
It's in that table where it lists all of the primary properties
This
of
one.
Portland cements. It says that C3S is 3 CaO times.
Like, will we have that in the exam?
Probably not.
No, you don't get it as an exam question, but you have got it as a tutorial question, because that understanding is needed. You don't need to remember this, but you need to have that understanding. So C3S, C stand for calcium oxide, S stand for silicon dioxide. C is there. Sorry, 3 is there. So here C2S, C stand for calcium oxide, silicon dioxide is S, and you have 2 because there is C2S. That, like, general understanding should be there. A is aluminium oxide and F is this. All these are oxides. A is this and C is this. So you need to have, like, you don't need to remember, but you need to have, like, that sense.
Yeah.
Okay, so last question. In the last question, I already told you this. I told you we have general purpose cement, we have general purpose limestone cement, we have general purpose blended cement, and also they are asking the abbreviations with these abbreviations, type SL, type SR, type LLH. So you can now tell me the answers for this. So some special purpose cements are listed below. Select the most suitable type of cement for each concrete construction application table. So you have to, which one you need to use for massive dam construction? High early strength, low heat, sulfate resisting, shrinkage limited. Which one is recommended, should be recommended?
Is it high early strength?
In a massive dam, you don't need to, like, you don't have that hurry to open, like, it's a big construction.
Would it be shrinkage?
Not really. I told you when we were discussing about this, about a massive dam, it's a huge amount of concrete. And I told you when concrete that reaction is producing a lot of heat, And when we have a massive concrete, if we don't control the heat, the outer surface get hardened quickly, and the inner material is slowly getting hardened, and it is and when you have heat, the material is expanding. When you have cool down, the same material, it will make like shrinking. So if you have in a massive dam, you have a huge amount of concrete, so this part will get hardened quicker, but the inner material is getting hardened slowly, and this will undergo different thermal expansions and contractions, outer surface and the inner material. So you need to control what?
The shrink.
Not
Low
the
heat. Cement.
low heat, isn't it?
But don't you also need shrinkage limited cement?
Shrinkage limited is this heat, low heat cement is needed to reduce the thermal cracks. Shrinkage is happening, so it's not the problem in the dam. The problem is the heat, thermal cracks.
Yeah.
Isn't it? But in the you have an application for shrinkage as well. I want you to find it. So do you agree with me? Here, the critical part is the heat, thermal cracks, not the size.
Yeah.
Shrinkage is important where we need the exact size. We don't want the shape to change.
Okay.
Are you agree, Haley? Do you agree with me as well?
Yeah.
Okay. So quick road repair, what do you recommend?
High early strength.
Higher
The higher list.
sewage pipeline construction.
Sulfate.
Sulfate resisting, because we don't want that cement to react with the sulfate and make the concrete swollen. Bridge and over shrinkage limited. Marine, again contaminated, like chemicals are there involved. Sulfate resisting. Yes, so that's good. Do you guys have any question?
No.
No, I don't have any questions, but I was just wondering about the intensives. On the timetable, it says that our pracs are on the last day. Is that true?
In the timetable, if it says like that, the rooms are already booked.
Yeah, okay.
We're doing the pracs after the exam.
Yes, so then in that case, yes, you need to you have to be in the class for the labs. The rooms are already booked. I will try to see whether we can do a change, swap the 2 days, last 2 days. I will check.
I don't mind. I just wanted to double check before Brea and I booked flights. That's all.
Yeah, in that case, it's safe for the safe side. Let's like just keep it as it is, and I'll try to. But it's uncertain.
Okay.
Yeah.
Thank you, Pika.
Okay.
Well, are we allowed to bring notes into the exam, or is it going to be like?
For the mid-quarter, no. Again, for the final exam, it is closed book.